In this chapter, we will talk about alkanes and all the properties of alkanes, their nomenclature, their isomers, and then eventually their physical properties, and then conformation analysis. I've divided this up into two. So in this part, we will just do the nomenclature, some constitutional isomers, and then talk about the physical properties. So first, let's talk a little bit about the structure for alkanes. All alkanes are considered to be hydrocarbons because they're made up only of carbon and hydrogen. They're also called saturated hydrocarbons because they're only made up of single bonds. And because they're single bonds, you have to think about carbon as being sp3 hybridized. So all the properties that go with sp3 hybridization are what is followed by alkanes. Alkanes are also saturated hydrocarbons, which means that all the bonds are single here, and alkanes are also the open chain ones or open chain structures. We will talk a little bit later about cycloalkanes in which they're in a cyclic structure, but these ones are straight chain. Alkanes are also referred to as aliphatic sometimes, as opposed to aromatic. Aromatic hydrocarbons are a different functional group, as you learned in your functional group. So alkanes are also referred sometimes as aliphatics. A little bit about organic structures before we go on, because from now onwards you will see structures in organic chemistry in different ways. So just a little review here. A molecular formula is just the number of atoms you have, and they're all given as a bunch, and so you really don't know what the structure will be like. A condensed structure is a little bit better. It's a little bit more, it shows a little bit the connectivity of each of the carbons to the different number of atoms that it has. And then in an expanded structure, you get to see all the carbons and the hydrogens, okay, in there. I couldn't draw out the carbons, but the carbons are all where these points are, okay, and then you show all the hydrogens in there. And then the line structure is when you don't show any carbon or hydrogen. So it's invisible, but they're all there. Okay, and so the way you figure out how many hydrogens you have is by looking at how many bonds you have on carbon. So if this is one bond on carbon, the rest of the three must be hydrogen. On this carbon, there are two bonds, so two must be hydrogen. So that's how you have representations. For most part, we represent in line structures because it's easier. You don't have to draw the hydrogens. But right now you will see all sorts of structures as we go on. Okay, so let's look at the nomenclature and go over some of the basic stuff that you would need for naming alkanes. First of all, let's look at the table on the left, which is number of carbons and prefixes. And the prefixes are really neat in organic chemistry because you can use any of these prefixes to indicate the number of carbons we have. Now remember, you have all these functional groups in organic chemistry, and all these functional groups have what we call homologous series. And in the homologous series, what you have is increments of carbon one by one by one. And so you can have a series going from 1 carbon to 24 carbons or even more. So there has to be a systematic way of knowing how many carbons you're dealing with, whether you're dealing with ketones or alcohols or alkenes. And so this is a systematic way of doing things, okay? And so the number of carbons will give you a prefix, okay? And so that prefix is what you use then for all the compounds, all right? So for carbon 1, the prefix is met. For 2, it's eth. For 3 is prop. 4 is but. 5 is pent. And after pent, it becomes a little easier because now it's based on math, okay? Which means 5, 6, 7, 8, 9, 10, pent, hex, hept, oct, non, deca. Okay, and so this is how the prefixes would be. These prefixes are used throughout organic chemistry, so it should be all the same thing over and over again. Here are the names for alkanes, and you will see two things over here. Okay, and the ones that I want you to note is the prefix, which is the meth. For example, the meth indicates 1 carbon. The ane, which is considered to be the suffix, is coming for the family alkane. Okay, and so as the family changes, we will change the suffix. but the meth, eth, prop will stay the same depending on the number of carbons there are. So for alkanes, meth, eth, propane, methane, ethane, propane, butane, pentane, hexane, so on and so forth. Okay, and it goes all the way there. I need you to remember from 1 through 10. That's what's required for you from this. Let's start with the nomenclature then. Okay, actually looking at a big compound, okay, and see the rules that you need. So the first rule of any nomenclature is you find the longest continuous carbon chain. Okay, so your carbon chain may be straight, it may be going up and down, it doesn't matter, but you find the longest continuous carbon chain first. Okay, then you number the carbons starting from the branching. Whether the branching is on the left side, right side, top, bottom, it doesn't matter, but that's where you will start numbering. When you look at branching, the branching has to do with any kind of an atom that might be attached, except for hydrogen, of course. But whether you have carbons or chlorine, whatever it is, that's where you would start the numbering. Okay. The third thing is that wherever you start the numbering from, that probably is where you will have the suffix. Okay, now down here you can see these are the basic things, okay, that you need for any kind of a nomenclature. You need a locant, which is a number. You need a prefix, which tells you what kind of groups you have, the parent, which is the longest chain, and then the suffix, okay, which is the functional group. All right, that is how you have a breakdown for any kind of a nomenclature. So that's the suffix that we are talking about in number 3. Okay, the longest chain, number 1, that's the parent, okay, that we are talking about. The locants will come from numbering, okay, of all these things. So suffix is the functional group, okay, that we talk about. Then you start naming the groups that are attached, okay, for each of the numbers. So for example, if you have 2 branches coming out in the longest chain, you go ahead and name the 2 groups, okay, whether it is chloro or whether it's methyl, ethyl, and we will learn these names also, okay, but you name all of these groups that are attached to the chain. Once you have figured out all the names, then you go ahead and alphabetize the substituents. That's the key thing here in nomenclature, is that you do not do this chronologically, you do it alphabetically. All right, so for example, if you have chloro, methyl, then chlorine will come first and then the methyl group. Okay. If you have 2 or 3 groups, then you will use di, tri, tetra, penta, whatever it might be, depending on what kind of substituents you have. So for example, if you have 2 chlorines, it would be dichloro. If you have 2 methyls, it would be dimethyl. If you have 1 chlorine and it's chloro, if you have 3 methyl, it will be trimethyl, so on and so forth. Okay, there is nothing like a mono in here. You start only from di. Okay, the di, tri, these things are not used for alphabetizing purposes. Okay, this is used only to tell you how many you have. So for example, if you had 2 methyl groups and would become dimethyl, that D is still going to come after C. Well, I guess that's not a good example, but if you had fluoro, then it will still come after F, okay, because technically the group is methyl and not dimethyl, okay. The di just tells you how many methyl groups you have, okay. So then finally, an IUPAC name can have up to 4 features, okay, which is the locant, prefix, parent, and then suffix, okay. These are the things that you need. Here's an example, okay, so here is a big long chain. This is where the branching starts because this is where the OH group is. If there was a hydrogen over here, we would start from the left-hand side. But because there is an OH here, this is where our branching is. So start from the right-hand side. This is 1, 2, 3, 4, 5, 6. Okay, so our parent is a 6 carbon, so which means a hex. Our suffix is the functional group, which is all. Okay, so hexanol. At least we know we have a hexanol. All right, and then you look for the branches, which 1, 2, 3, 4. On the 4th carbon, there is a methyl group. Okay, 4 is the locant, methyl is the prefix, 1 hexanol. The 1 tells you the location of the OH, and you're probably thinking, well, that's where we started the numbering from. But you still have to give the number, okay, just to be sure and be exact. Even if you said 4 methyl hexanol, it's not wrong because it's assumed that it's going to be on 1, but you should still write 1. Okay, IUPAC expects you to write 1 there. So then this name is 4-methyl 1-hexanol. Now please note here that between the number and the letter is a small dash. Between the letter and the number is a dash, and that's how you do it. Okay, so if we had 2 groups, then we have to use more dashes and some commas also, which will come up later on. But these are some of the rules for nomenclature. Okay, so this is for alkanes. By the way, what we're doing here, this is called the IUPAC nomenclature. People call it IUPAC. I just call it IUPAC. But this is the systematic nomenclature. Okay, and it is very systematic. Typically, if you have a name given to you, you can figure out exactly what the structure is. This slide is a keeper, okay, and this will be very helpful for you in the beginning. Later on, I know you will get used to it, but in the beginning, you really need to have this handy and memorize all of these, okay? You just have to. And as I said, it will come easy to you afterwards. Alkyl groups. These are the most common substituents, okay, that we have. All the other substituents that we'll come across, I will go over them one by one. But alkyl groups are very specific because you find them all the time. An alkyl group comes from alkanes. Okay, you remove one hydrogen and it becomes YL at the end. So alkane minus one hydrogen is equal to alkyl. All right, so as soon as you see an ill anywhere, it means that it is attached to something and it is an alkane-like thing minus one hydrogen. Okay, so these things are called substituents. And a lot of these alkyl groups, most of them will go only up to 4 carbons, okay, because after that it starts getting complicated. So we try and limit it only to 4 carbons, sometimes 5. There's only one for 5 because after that there is another way of doing it. But these are up to 4 carbons, okay, and so the first one, this is the methyl group. Remember, CH4 is methane, so minus 1 hydrogen will give CH3. This little dash here indicates that this group is actually connected to something. So this is called a methyl group. Methane, methyl. Okay, so that's what this group is called. Now the short form for this group is Me. This is written just like any kind of a chemical symbol, which means that the first letter is capitalized and the second symbol is not capitalized, it's small case. You will not find these abbreviations on the periodic table. Okay, so don't even look, or you can look if you want to, but you will not find them. Okay, that's the nice thing about these ones. So anyhow, this is the first one, methyl group, which is Me. The second one is ethyl group, which is Et. Remember over here, this should have been CH3, but it's actually CH2, all right, minus one hydrogen. The next one is a propyl group. Okay, with propyl group now there are 2 things possible. Okay, the 2 things that are possible with propyl is that you can have the connection at the end carbon, or you can have the connection at the middle carbon. Okay, which means instead of the connection here, you can have the connection here. Now these 2 then, these are called constitutional isomers, okay, of each other. And even though these are alkyl groups, these are still constitutional isomers because they share the same molecular formula. So, but we have to give different names to this. So the first one, which is a straight chain, is called the N-propyl, normal propyl. And the one that is coming out in the middle, or that's connected in the second carbon, is called isopropyl. And the short forms of these are NPR and IPR. Okay, now the I here is a small case because that only shows how the linkage is. The actual group is actually PR, okay, the propyl group. What I've also given you over here are some line structures of how these things are drawn out. For methyl group is just one straight line. Okay, I didn't want to draw it out and confuse you, so it's just one straight line. For ethyl group, there are 2 carbons and here it is connected right here. And then here for propyl, for N-propyl, it will be 1, 2, 3 carbons connected right here. Okay, so this bond, this belongs somewhere. Okay, it's broken, poor thing. And then here we have the isopropyl. In case of the isopropyl, see the connections in the middle. And I want you to look at this V, okay, kind of a thing, because wherever you see this kind of a V, that means it's an iso kind of a group, all right? Okay, so these are up to up to 3 carbons. Now we go to the 4 carbons. Now since we have 4 carbons, we will have more isomers for this one. With propyl we had 2. With butyl we actually have 4 isomers. The first one is the normal butyl group, which is connected to the end. 1, 2, 3, 4. 4 carbons, which is connected somewhere. It's called N-butyl, normal butyl, NBU. This one is called secondary butyl, which in this case, or you can call it second, but secondary is the right name for it. And in this case, the bonding is actually on the second, which means the connection is on the second carbon. So here, this is what it looks like. Okay, this is called sec-butyl. And then you can take the sec-butyl, or actually you can take the N-butyl, and then move one of the carbons, and this gives us what we call isobutyl, IBU. And here look at the iso, the V. Okay, you can still see that. Now we still have 4 carbons. 1, 2, 3, 4. Okay, so we still have the 4 carbons here. So this is called the isobutyl group. And then finally, this is called the tertiary butyl group, which actually looks like a T. So the T-butyl really goes well with it. Okay, so I've drawn this in a proper angle, but otherwise this would be a perfect T. Okay, and that's the T-butyl group. And then finally here, we have a neopentyl group, and I drew this out just so that you kind of know what this is, but typically we don't have that many alkyl substituents for 5 carbons. Okay, this is the only one that is used a lot, and this is 1, 2, 3, 4, 5. So neopentyl, the way I remember neo is of course from matrix. Okay, so anyhow, it's like T-butyl except one more carbon. Okay, over here. What we have on the left hand side are phenyl groups. Okay, and these are coming from benzene. Benzene is C6H6. Okay, benzene minus 1 hydrogen gives us C6H5. So again, just like an alkyl group, benzene can also be connected to something, and this is what it would look like. Okay, where you have a benzene and a bond coming out, which means that this is connected somewhere. Okay, this is just with the ring, but these two are the same things. C6H5 connected somewhere, and then the most short form of a phenyl group is pH. Okay, and these are called phenyl group. All right. If you want to be a die-hard chemist, then a die-hard chemist draws their benzene like this, which is the symbol phi. So phi H is benzene. So phi connected to something is phenyl group, and then AR, which is arene ring, is used only if the benzene ring has any kind of substituents. If it does not have any substituents, which means if it's just a plain old benzene ring, then you would use pH. Okay, for that. These are all the alkyl substituents that you need for organic, and please memorize all of this. There is one more nomenclature that I will do for all of these in one of the later slides. Now for some simple nomenclature. Okay, we'll take it step by step now that you know the basics, okay, of everything. So let's take it small steps, okay, at a time. So here we have this compound given to us. Now usually if you have this kind of a structure given, remember this is kind of like an expanded structure, but not quite. Okay, so the best thing to do is make it a line structure. Okay, so you can see things clearly and you can see the longest chain that way. So this one is the longest chain is 1, 2, 3. It could also be 1, 2, 3, or it could be 1, 2, 3. So in no matter from where you count, it's still 3 carbons. So let's just take it the horizontal way. Okay, 1, 2, 3. On the second carbon, you have a methyl group coming out. So it becomes 2-methyl propane. Now note, there is no space between methyl and propane. There is a dash between 2 and the alphabet, all right, but no space between methyl and propane. If you leave a space, it's not terribly wrong because it kind of looks odd when you say it, but the thing is, well, once you get used to the naming, then you know that this is methyl and that's propane, all right? Okay, here is another one. And now this example here is about numbering, okay, where you start the numbering from. So here are 2 options for you, okay? Once you draw this compound in the line structure, you can see that the branching starts from the right hand side, Okay, so which means that this numbering 1, 2, 3, 4, 5, this is the correct one. This will be incorrect, 1, 2, 3, 4, 5, because you should start numbering from where the branching starts, okay, not from the other side. So 1, 2, again on 2 there is a methyl group, so 2-methylpentane. That will be the name for this and not 4-methylpentane. Initially, when you're working on nomenclature, I'm going to give you some wrong names. So that way you get to practice and see what is wrong with a name, okay? Because if you keep seeing the right names all the time, then you sometimes don't know what you're doing wrong. So I will give you some wrong ones also, okay? So you can figure out what's wrong with it. These examples over here are again about numbering, okay, and how you do that. Now in this case, we have two substituents. In the previous slide, we had one substituent only, but now we actually have two substituents. Your fundamentals should still be the same, which means that you figured out the longest chain, which is 1, 2, 3, 4, 5, 6. It could be 1, 2, 3, 4, 5, 6 going up also, but it's still the 6, so keep the horizontal one as your main one. Now, since you have two substituents over here, you have to decide where am I going to start numbering this chain from the right-hand side or from the left-hand side. And because the branching is from the right-hand side, you will start numbering from the right. Okay, so 1, 2, 3, 4, 5, 6, not the other way, not 1, 2, 3, 4, 5, 6, because here your substituents will get a higher number. Okay, your substituent should always have lower numbers possible. Okay, that is the rule of IUPAC. So now you have two substituents, both of them are methyl groups. So you give the two locants where they're located. So 2, 4. All right, so they're located on the second carbon and the fourth carbon. And since you have two of the methyl groups, you will write dimethylhexane then. Hexane is your parent chain. Okay, that's the base. Between 2 and 4, you have to put a comma. So between two numbers, you have to put a comma. And again, number and letters are separated by a dash. You have to say di, by the way, okay? Just because you're saying that you have 2,4 doesn't mean that you have two. You have to say 2,4-dimethyl, not 2,4-methylhexane, okay? The di is necessary over here. Okay, so this is about this compound. This example over here is for when you have a different substituent. Okay, then when do you, where do you start numbering and how do you write it out? Okay, so in this case, you have a long chain and the long chain is of 7 carbons. Again, we can count it 1, 2, 3, 4, 5, 6, 7. We can have 1, 2, 3, 4, 5, 6, 7. Again, since both of them are 7 carbons, we should keep the horizontal one at our base because that is easier, okay, to remember. The two groups that you have are a methyl group and an ethyl group, okay, over here. Now, you have to figure out where am I going to start numbering from? Is it the left or the right? So you look at the substituents. Where is it coming out first? 1, 2, 3, and you have an ethyl. 1, 2, 3, and you have a methyl, all right? So what you will do is choose the ethyl first because it comes alphabetically, okay? So in this case, the third carbon is where the substituent is, okay? So the only question now is, do I start on the left and the right? And if you start from the right, then you're breaking the rule of alphabetization, okay? So alphabetization first, okay, because they are equidistant from either side. So which means 3-ethyl, 5-methyl heptane. So in this case, what you do is you obey the two rules, which is that your alphabetization is correct as well as you get the lower numbers also for the group. Okay, so this name here starting from the right hand side is not correct. Okay, you have to give the lower number to the lower alphabet. Okay, that's how it goes. Now in this case we have a little bit more substituents. Okay, so here we still have the ethyl group and we have the two methyl groups, but see in this case the ethyl group is on the third in the third carbon, whereas our two methyl groups are on the second carbon. So we have to give this one preference, okay, because we have two branching going on the left side. So this will take preference now, okay. If you had two branching going on over on the third carbon, then you will still give the preference to the ethyl. Okay, but because it's on the second one, you will give preference to carbon number 2. Okay, so then you number from the left hand side 1, 2, 3, 4, 5, 6. On the second carbon 2,2-dimethyl. So even if you have the same number, you have to say it twice. You have the same group, you still have to say it twice, dimethyl. Okay, so make sure that you do that. And then of course on the fourth carbon we have the ethyl. The ethyl will come first, not the di, because remember di is only a quantity. It is not the name of the substituent. The substituent is still methyl, so alphabetically speaking, ethyl will come before methyl. Okay, the di again, remember, is just a number. All right, so again 4-ethyl-2, 2-dimethylhexane. Okay, that would be the most lovely name of this compound, and this is IUPAC name. And so if you have more substituents, you have larger compounds, then the name gets larger and larger. That's how it becomes. Here are some common names that you can look at, and usually you will not encounter them. Butane is a common name, of course. Butane is the IUPAC for 4 carbon, but if you have a branching going on, which if you remember it was 2-methylpropane, this is also called isobutane. With pentane, there is the isopentane, which remember is the V over here, that's the isopentane, and then the neopentane, okay, which gave us the neopentyl group. So these are some of the common names. Maybe you will see them, maybe you won't. I don't give them on the exam. I usually prefer the IUPAC name, okay? So don't have to worry about it for me. Here are some more examples, okay, for you to look at. I will not go through all of them, but look at all of these and see if you have any trouble or if you're encountering anything that you don't understand, then I can help you out, okay, because we will do this in class. So look at the numbering, look at the long chain and how it goes. This is quite twisted, which is kind of what I do to you. I'm sorry for that, but this is how compounds usually are once they get larger and larger. So again, the fundamental is finding the long chain first. Once you have the long chain, then you start numbering from the closest to the branching, okay, and then you identify all the substituents, okay. So that's kind of what you have to do. So in any case, look at this yourself and then let me know if you have any issues. Classification of carbons and hydrogens. This is also an important part of organic, is to understand how things are connected. I've been talking to you about constitutional isomers and how connectivity is the most important thing. And here again, connectivity makes a big difference. Okay. So if you have a carbon bonded to just one carbon, that is called a primary carbon. And a primary hydrogen is one that is bonded to a primary carbon. Simple as that. A secondary carbon is bonded to 2 other carbons, and a secondary hydrogen is bonded to a secondary carbon. Okay, I will not say that again. It gets repetitive. Okay, so you understand that. Anyhow, tertiary carbon is the one that is bonded to 3 other carbons, and a quaternary one is that is bonded to 4 other carbons. So here, let's look at this one. So for example, this red one, this pink one over here, this is bonded to just 1 carbon and therefore it's primary. This carbon now is bonded to 2 carbons. It doesn't matter what kind they are. It doesn't really matter. It could be a long chain, short chain, who cares, all right? But the important thing is it's bonded to 2 carbons, and so that's all that matters. That's what makes it secondary. Tertiary is when you have 3, and quaternary is when you have 4, okay? Now, for the hydrogens, this is a primary carbon, these are primary hydrogens. Secondary carbon, secondary hydrogens. Tertiary carbon, tertiary hydrogen. Quaternary carbon, no hydrogens, okay, because carbon already has the 4 bonds. Now, we talk about the hydrogens here, but groups can be the same way. So for example, if there's a chlorine on here, that chlorine can be tertiary. If there is an OH over here, a hydroxy group, an alcohol group, then that alcohol will be secondary, and so on and so forth. So that's the secondary, the primary, all of these are coming actually from the connectivity of the carbon, okay, of what that carbon is connected to. So here's an example, okay, of this kind of a compound. You should be able to see this from a condensed structure, but if you're not, then you should go ahead and expand the structure so you can clearly see what kind of hydrogens we have. So here, the first carbon, this is all the pink hydrogens. These are all primary. This is a secondary carbon because it's connected to two carbons. This carbon here is connected to 1, 2, 3, and so it's tertiary. This carbon is primary because it's connected to only one, and then this carbon is primary because it's connected only to one. This is connected to many others, and that does not matter. When you're looking at this one carbon, just focus on that, okay, and see what it is connected to. And then, of course, the corresponding hydrogens. All the pink ones are the primary because those are the primary carbons, and the blue ones are the secondary because this is a secondary carbon. This is a tertiary hydrogen. This slide is a little bit about some general nomenclature. In Organic 1, we are focusing more on alkanes, alkenes, and alkynes, but you will still encounter some alcohols and some haloalkanes. So you need to know a little bit about the nomenclature of that. Not a whole lot, but at least you should be familiar with it. So the next few slides are just to make you familiar with all organic nomenclature. So when you come across something, you're not completely shocked, okay, as to what is this? I've never seen this before, okay? So I don't want you to think like that. I want you to take it systematically and then figure out what these names are, okay? So again, the prefix tells us the number of carbons, infix tells us the nature of carbon-carbon bonds, and the suffix tells us the class of the compound. Now, this is not as different from what we were talking about before. Now, this is getting a little bit more complicated. Okay, that's all there is to it. So anyhow, when you have something like an ane infix, that means you have single bonds, ene, double bonds, ine, you have triple bonds, okay, in there. Could be one or more. You can't tell unless you look at the name of it, okay, but just the base name will give you an idea, okay, of what's going on. The suffix will tell you what kind of a class of compounds you're talking about. So methane, since it's ending in E, it's a hydrocarbon. Methanol would be an alcohol. Methanol would be an aldehyde, and then amine, ketone, and so on and so forth. Okay, so if you keep it systematic, it's not really very hard to do. Okay, that's organic nomenclature, very systematic. Here are some examples for the nomenclature then. And again, these are just a general idea. So when you look at a structure, you're not completely shocked. Okay, so here we have propene. So when you look at propene, you know you have prop, 3 carbons, ene, and alkene group. Okay, now it doesn't really tell you where the alkene is, and that is because there's only 2 locations for it, which will still give you the same compound. But when we get to alkene nomenclature, we'll have to specify where the double bond is. Right now, this is just a general idea. Okay, then ethanol. Eth tells you that you have 2 carbons, and the ol tells you that you have an alcohol group. Okay, so here is the structure, CH3, CH2, OH. Butanone, without looking at the structure, you should be able to say that you have 4 carbons, and on is for a ketone. Okay, so that's what the structure would look like. Butanal, but, 4 carbons, al would be for an aldehyde. Okay, aldehydes are terminal, so you don't have to number them. That's the nice thing about aldehydes. The same thing goes for carboxylic acids. Carboxylic acids are terminal. And so for pentanoic acid, you know you have pent as in 5 carbons, and then oic acid tells you that you have a carboxylic acid. Cyclohexanol, okay, cyclo is a cyclic, which you're going to do in the next slide, is a cyclic compound. Hex means that you have 6 carbons, and all means that you have an alcohol somewhere. Ethine, eth tells you that you have 2 carbons, ine tells you you have a triple bond. Ethanamine, okay, eth, 2 carbons, amine, and amine group. Okay, it's usually as simple as that. There are a few other things that we have to talk about as we go through nomenclature, but otherwise, keep it simple. Now for the cycloalkanes, okay, things are a little bit different for cycloalkanes. Cycloalkanes are rings, okay, of carbons. They're cyclic and they're anes, which means that you still have all single bonds, okay, in all of these structures. The formula for cycloalkane is CnH2n, which is actually similar to alkenes because it is minus 2 hydrogens. So as soon as you go from an alkane to a cycloalkane, you lose 2 hydrogens, okay, to form that ring in there. The cycloalkane usually is the base compound. The only time it's not a base compound is when the ring is small and the chain is longer. Okay, and then we'll go through some examples and you will see how you can use that. Okay, you have to number the carbons in the ring if there is more than one substituent. If there is only one, it doesn't matter. The first alphabet goes to the lower number, okay, if you have more substituent. We follow kind of the same rules as we did for the other ones, which is the alkanes, which means that you start from alphabetically. So if you have an ethyl group and a methyl group, you give ethyl group the lower number. Okay, that's kind of how it goes. And here is how you decide. If you have a long chain, then you will use the long chain as your base and the cycloalkane as a cycloalkyl group. Okay, so that's how it goes. Here are some of your basic chains, basic rings: cyclopropane, 3 carbon, cyclobutane, 4 carbon, cyclopentane, cyclohexane. It's very rare that you will encounter cycloheptane or octane. Okay, those occur, but not so much. We will talk about them in class, but naturally occurring rings are pretty much cyclopentane and cyclohexane. Here are some examples of nomenclature for cycloalkanes. So let's just go through the names of all of these really quick. Here is a cyclopentane, which has an isopropyl group attached to it. So it's isopropyl cyclopentane. I gave it a little space over here. I know for those of you diehard IUPAC nomenclaturists that, there should be no space. There should be no space, but I separated it just for your convenience. But isopropyl cyclopentane. Okay, so don't forget the cyclo. All right, this is the most commonly missed out word, okay, when naming cyclo compounds. Here we have 2 substituents. So we have a methyl group and we have a T-butyl group, and the butyl, okay, is the substituent, and so the butyl goes first. So that also gets the first number. So 1, 2, 3, 4. 1 T-butyl, 4 methyl, and the ring is a cyclohexane ring. That's how this one goes. If you have 3 substituents, you always number towards the lower numbers. Okay, that is how it will go. So for example, the numbering here is starting from the ethyl group because that is the lowest one alphabetically speaking. So start from here: 1, 2, 3, 4, 5, 6. Okay, this is the way to do it. I'm going to do the wrong way now. Okay, 1, 2, 3, 4, 5, 6. That's the wrong way to do it. Again, always give lower numbers to all the substituents. So 1 ethyl, 2, 5 dimethyl cyclohexane. Okay, that is how the name should be. Don't forget your commas and your dashes. Okay, all of them. Here's a really teeny tiny ring, cyclopropane. And here we have 1 ethyl, 1 methyl, cyclopropane. And finally over here, this one I gave a different kind because I want you to see how do you decide whether to give the cyclo group its own name, which is a cyclopentyl, like as a substituent, because now the base chain is longer. Okay, so this is 1, 2, 3, 4, 5, 6, 7 carbons. So that's heptane, and the cyclopentyl ring is on the second carbon. So again, instead of pentane, it becomes ill. And as soon as it is ill, it is a substituent. Okay, so that's how you would name this one. When you get to cyclic compounds, we also have what is called the cis and trans isomerism. And this is not quite constitutional isomer. This is a branching of constitutional isomer. Okay, cis and trans is when you have 2 hydrogens on the same side, and trans is when you have the 2 hydrogens on the opposite side. Okay, it has to have hydrogens in there. You cannot do it with any other groups. So if you have 2 hydrogens, and if those 2 hydrogens are on the same side, then that is called cis. These bonds that you see, the wedges, this one is coming out of the paper, the dashed line is going behind the paper, the straight lines, these are in the plane of the paper. Okay, so that is how we have the 3D structures, and we'll learn more about that also a little bit later. But anyhow, just to make sure that you understand what we have here. Cis and trans isomerism is also known as geometric isomerism. These bonds in cyclic compounds cannot rotate, and that is why these hydrogens are stuck the way they are. So this compound, which is a cis 1,2-dimethyl cyclopentane, is going to be different than trans 1,2-dimethyl cyclopentane. It will have slightly different properties. Now let's look at a class of compounds which are called the bicyclic compounds. These actually have two rings that are fused together, not connected by a bond, but fused together. So when you look at a bicyclic compounds, you really cannot tell where a ring starts and where the other one ends or starts. Okay, and so the nomenclature becomes a little bit different for this. First, there are two different kinds of carbons, a bridgehead carbon and a bridging carbon. Just pretend that there is a river over here and there is one starting point here and one ending point over here. So a bridge will start from this bridgehead carbon, take you to the second part of or to the other side of the river. Here is a direct bridge, and then here again is a third bridge. Okay, so there are three bridges that can take you to the bridgehead carbon. Okay, and then vice versa, of course. So there are bridgehead carbons and then there are bridging carbons. The bridging carbons can be 0, 1, 2, 3. It depends on how long the bridge is. In this case, you have two bridging carbons. Here, there's only one, and here there are two bridging carbons. Okay, this is what the structure would look like if you were to draw it in a line structure. So the six-membered ring is just like that. But the middle carbon, you have to show that at an angle, because if you draw a straight line, it doesn't really quite show that you have a carbon there. So you have to draw it at an angle. This really is what the structure looks like, okay, in 3D, in reality. This is how it exists, okay? So just take this molecule and turn it around 90 degrees, and this is what it will look like. For me, it's okay if you draw it this way or this way. It doesn't matter, but this is reality, okay? This is how it exists. Now for the nomenclature part of bicyclic compounds, is actually quite fun. You count the total number of carbons you have in a ring, actually in the entire compound. So in this case, it is 1, 2, 3, 4, 5, 6, and then 7. So you have heptane as your base name. Bicyclo is what is given to start the nomenclature because it's a bicyclic compound. Okay, so you have to be able to differentiate between just cyclic compound and a bicyclic compound. So you have a bicyclo. Heptane is the total number of carbons. Okay, now remember, any kind of a bicyclic compound can have only two bridgehead carbons. Okay, bicyclic compound, only two bridgehead carbons. The rest of them are all bridging. Okay, so now what you do is you draw the square brackets and then you write down how many bridging carbons you have. So you have 2, 2, and 1. Okay, bridging carbon. So 2, 2, 1 is your bridging carbons that you have. By the time you do it the other way around, which means if you take the name and draw the structure, you will see that you will not go wrong, because what is not accounted over here is your bridgehead carbons, because it is understood, okay, that they are there in the name. Okay, if you have substituents on the rings, okay, then you have to number the largest ring. Now in this case, we don't follow the same philosophy that your substituent should have the lowest number. Here we follow the philosophy that the largest ring has to be numbered first. Okay, so the numbering will always start from the bridgehead carbon, and then you start numbering the larger ring. Remember, this is the smaller ring. This is a 5-membered ring. This is a 6-membered ring. Okay, 1, 2, 3, 4, 5, 6. So you number the large ring first. So 1, 2, 3, 4, 5, and then you go to the smaller one, 6, 7, and then to the one bridgehead. So which means you take the more bridging carbons, then the less, and then the least. Okay, so you go down from largest to the lowest number of bridging carbons. And it happens that our methyl is attached to the 8th carbon then. Okay, and so you have 8 methyl bicyclo 3 2 1 octane. Okay, octane is the total number of carbons in the ring. The methyl group is not part of the ring. It is a substituent which we named over here. Okay, so keep it separate. All right, here is another example. And in this case, you have a methyl group also over here. Now, the largest ring is this one. The second is this one. And look at this. This bridgehead carbon and this bridgehead carbon, they're connected with no carbons, okay, in the middle here. So 1, 2, 3, 4, 5, 6, largest ring. Then the next one, 7, 8, 9, okay, which means your total number of carbons is 9, which is nonane. The substituent is on the 8th carbon, so 8 methyl bicyclo, 4 bridging carbons, 3 bridging carbons, 0 bridging carbons. And even if you have 0 bridging carbons, you still have to write 0, okay, because it's a bicyclic compound, so you have to write that out. So that's how you would do for bicyclic compounds. Here are some examples, okay, of all types of compounds. And I wanted to give you an idea here of the different kinds of substituents, number of substituents, and of course we haven't dealt with chlorine yet, so or any kind of halogens, but halogens are fluoro, bromo, chloro, iodo. That's how they are numbered, that's how they are said. And so giving you some examples of that one here. This one here is of an alcohol. If you have an alcohol, you have to give it preference, okay, whether whatever kind of groups you have, it doesn't matter. Alcohol always gets number 1, okay, so keep that in mind. And then here, this one, the longest chain is the pentane, so use this one as a substituent. And here you have 2 rings that are connected by 3 carbons. This is what I meant in the previous slide when I said that they're not connected by a bond. The 2 rings are fused to give bicyclic compound. So this is not a bicyclic compound. These are just 2 rings that are joined by bonds. Okay, so go through all of this nomenclature and then we'll practice some more in class. Now for some physical properties of alkanes. Alkanes are the true hydrocarbons in organic chemistry, and they have only carbons and hydrogens. The most important intermolecular force in them is dispersion force. Okay, there is no dipole moment, there is no hydrogen bonding, so it's just dispersion forces, okay, in them. So the trend is that the boiling points and melting points will increase as the size of alkanes increases because dispersion forces are increasing. Why is the dispersion force increasing? Because the whole molecule size is increasing. If the molecule is increasing, it's because of the number of atoms you have in there. So the more electrons you have in there, the more protons you have, then it causes more of a dispersion force. Okay, and so that's kind of how it goes for alkanes. So as the size increases, remember boiling point and melting point increases. Then straight chain compounds versus branched alkanes. Straight chain compounds will have a higher boiling point because of a larger surface area. Okay, and then branched alkanes will have less. We'll see that in the next slide. Cycloalkanes have similar properties to alkanes. Okay, they're not as different. So here is a little chart to show you how the melting point and boiling points are increasing as the number of carbons are increasing. So constitutional isomers, here is the list of branching versus non-branching, okay, of compounds. So constitutional isomers of C6H14, so which means 6 carbons. It could be hexane, it could be pentane, depending on the branches that you have. So the important thing that you want to look from this table is, first of all, the structure formula, okay, because these are the different constitutional isomers that you can have of C6H14. So you start with a long chain, start with 1 branching, the branching moves over, and then you have 2 branches, and then you have this really not complex branching, but a really bulky kind of a structure, okay. So look at the boiling points of all of this. The boiling point here is 68.7, and then as the branching increases, the boiling point goes down. Okay, and again, this is going down because this compound here, hexane, is a straight chain compound, has more surface area, and therefore has better intermolecular forces than a branched one will. Okay, so just think about, if you were layering something, then you would want to have straight layers, because if you had things coming out of that layer, they would not be able to get as close. Okay, so that's what the boiling point, this is the most important column, okay, in all of this is the boiling point. So as the branching increases, the boiling point will decrease. And this is a very common question that you will get in an exam, is that I will give you a whole bunch of different constitutional isomers, and you have to figure out which one has the lowest boiling point or melt. Just another little slide about constitutional isomers. We've already dealt with this before, but as the molecular formula increases, the number of constitutional isomers increases. I'm sure there is a formula for this, but I don't know what it is. Okay, but you can see that the number of constitutional isomers increase a lot. Okay, by increasing just one carbon. Okay, so I don't have the formula, and it doesn't really matter. And trust me, I will never give you C40H82 to draw out. Okay, to draw me all the formulas. That's not happening. One last thing to mention about alkyl groups and their nomenclature is an alternate way of naming. Okay, and this is IUPAC accepted. The other one is also IUPAC accepted. So for example, if we have isopropyl group, isopropyl is IUPAC accepted. Okay, however, there is another name for it, which is called the 1-methyl ethyl. And here what we do is wherever it is connected, that carbon is numbered 1, and then you take the longest chain from there, which is in this case 2 carbon chain, and then whatever substituent is attached to that, that is named. So on the first carbon, there is a methyl, the longest chain is ethyl. Now remember, this is not ethane, this is still ethyl, okay, because this is connected. And usually you would write this in brackets because it shows that it is actually connected to something and not independent on its own, because it's not. Okay, it cannot exist on its own, it has to be connected to something. Let's take another example here for butyl, and butyl groups are really well served by this because it eliminates all sorts of connectivity problems. Okay, so we have 1, 2, 3 as the longest chain, and that is because the connection is right there. The branching starts over here, but remember, this has nothing to do with the branching. This numbering has to do with the connection. So if the connection is here, then the numbering start from that carbon. So find the longest chain, 1, 2, 3. So which means that the base is propyl, and on the first carbon there is a methyl coming out, so it's 1-methyl propyl. Okay, so sec-butyl can also be called 1-methyl propyl, and isobutyl can also be called 2-methyl propyl, and a T-butyl group is then called 1,1-dimethyl ethyl. Okay, so that's an alternate way of naming alkyl groups. Now I mentioned to you before that usually we don't have groups for 5 carbons, and that again is because if you have sec-pentyl or isopentyl, it becomes a little confusing. So in those kind of cases, this nomenclature is very helpful. For butyl group, there is no other name because there is no branching, so you don't have to worry about that. But I wrote it out just so that you kind of know this. So finally, our keywords and our concepts for this chapter are the nomenclature for all alkanes, cycloalkanes, and then bicycloalkanes. You should know constitutional isomers. You can never, ever, ever forget that one. The cis and trans isomerism in cycloalkanes, we will do this more in the next in the next part also. But still, just was just a little bit of an introduction for you. You should be able to write all the different kind of representations for organic compounds. I think you're getting comfortable in this one. And then, of course, know all the alkyl groups, okay, and phenyl group, and then little idea of the physical properties of alkanes.